Hello again, everyone. So it turns out I also work at Fermilab for the HEPCloud group. So this talk will be a bit of a different take on the previous one. The previous one, we were talking about something that we're currently developing. This is more of a report of some work that we did on the HEPCloud Split Starter. Some of you might recall from, I think, a couple of weeks ago, Maria has been here in person talking about the work that she did on the HEPCloud Split Starter. And basically, the work that we did now was generalizing what she had already done for a couple of sites and make it more general and reusable across different sites. So first, let's talk about what the Split Starter is. So it's actually, so it's nothing new. The Split Starter is an extension of the HTC23 Split Starter, which is a work that the Conda team had started, and we just expanded on it to use for our use cases. I decided to call it HPSS, which, saying out loud, just made me realize how awfully close it is to HTCSS, but I'm pretty sure it won't generate any confusions here. So why do we need that? Well, the main goal here is that we need to run jobs on HPC sites, right? Ideally, we want to run jobs on HPC sites using the infrastructure that we already have deployed, HEPCloud, based on HTC23. However, HPC sites normally will block internet connection on their worker nodes. And that's an issue for the starter, right? Because you need first to download the job payload. Once it's finished executing, you need to upload it back to the SCAD, which again, if you can't talk to the world outside, there's no way you can do it. So the way the Split Starter solves this issue is actually pretty smart. What we do is that we basically split the starter in an edge node or a login node, which is something that hopefully we can request from the HPC site we're trying to run on. And then we start another portion of it on the worker node. So the way it works, and I'll expand a little bit more on that, but basically, we have it started on the edge node, which will talk to the SCAD. These guys here will be responsible for downloading everything that we need from the SCAD and uploading it back. The starter on the worker node is a part of it actually doing the work. And the way we transfer data from here to here is basically through a shared file system. There's another issue, which is if we can't access the internet, we can't run Glide inside. And because of it, we need to provide, along with the job itself, we need to provide a set of other tools that we will need to set up the environment for our jobs, our experience jobs. Stuff like configuration files, containers, custom scripts, all that needs to be sent along with the job. Also, HPC sites often do not use Conda. So we also need some scripts to interact, at least for basic operations, with the local batch system. So operations like submitting jobs and querying the local queue also need to be implemented by this solution. So in the previous work, we had it working on Theta for a couple of experiments, M2E and CMS. And it worked really well, actually. We were able to submit jobs there. They run just as expected. We had all components we need for those two experiments. However, the problem with it is that the implementation that we had at the time was very coupled to the site itself and the experiments it was running on, or for, should they say. So now, if we needed to support new sites or experiments, we would have to basically replicate a bunch of code that we already had for those two experiments. And the reason for that was when the Split Starter was first implemented, it uses some templating system, which is actually a very good idea. I'm still using it. But the problem is that this template had a lot of code. It was a very heavy template that would have all these components that we mentioned before, the scripts, tools, and configurations here. They would all be within this template, kind of coupled to the code we had there. And I chose a good word here, like embedded. I decided it was better to say embedded than hard-coded. That's basically how things were developed on those templates. So last year, we decided to start running some tests on Summit on Oak Ridge. And of course, we needed a way to submit jobs there in a more automated way. Right? So we decided to use HPSS as a convenient way of sending the jobs there. So to do that, we would have to implement support for Summit, right? So we had a couple of options here that we had to think about. Either we would reuse the same model that we had before, which is replicating that template and making the code changes that we would need to make sure it would run on Summit for CMS, which was the experiment in question we were trying to run jobs there. Or we could generalize the Split Starter implementation and make sure we would do it once, and we would then be able to run across several sites for several experiments. Of course, that's the option that we ended up choosing just because the previous one wouldn't scale. But even then, we had to think how we would do that, right? So we had a few options. We could use the same template model that we already had, just make it more generic, try and decouple the experiment and site-specific components of it from the code. Or we could try and rebuild part of it, use something like Flap, for example, at least for the interaction with the local batch system on the HPC side. Or we could just start from scratch, implement something new in Python, for example, and use Radical Saga tools, for example, to try and achieve the same purpose. Last year, our main concern was the time constraint that we had. So we decided to go with the first option. Also because that would mean we would have to re-implement the least amount of code possible. So we could reuse as much of the previous implementation as we could. So as I said, I actually kept the templating system that we already had, just made it a bit more general. So the main idea is that we would have a couple of components that we would need. So we would need a few, or should I say a couple of groups that we would need. We would need something to specify the experiment needs, and something else to specify the site needs, or mostly the batch system needs, right? So what we actually ended up with is scripts that will be used by the main workflow of the application, that will use standardized directory trees, which are just really repositories, hopefully something like GitHub or GitLab repositories, that will just based on that to run on specific sites. So in addition to it, we'll have also a configuration file for that specific site and experiment pair, which we'll from now on call account. So basically, whenever I say account, I'm referring to a specific experiment running on a specific site. And that's basically the model we ended up going with. So besides this repository with the account configuration file, we would also need some specific set of scripts to interact with the batch system locally, since we don't have a Flap solution. And hopefully the experiments will only have to provide these repositories and one configuration file to be able to run in any supported site with or should I say, on any site that supports the batch systems that we have implemented. So let's start talking about these batch system scripts that we have. So right now we support 3 batch systems, which are Cobalt, OLCF, and Slurm. And there are really only 4 operations that we need to run these scripts. So we need something that creates a submit script file. We need something that checks how many jobs we have in the queue for a given user, what jobs are in the queue, and something that submits the job with this submit script that we just created up here. That's all we need. So if tomorrow we need to support a new batch system here, we only need to find a way to implement those 4 scripts in a way that is compatible for the given batch system. And that's it. We would be able to run on a site that supports that batch system. The next part of it are the VO repositories, right? So this is an example here of what we have for CMS. Hopefully, the experiment will be able to provide everything that they need. That includes configuration files, maybe some containers, startup and wrap up scripts if they need to execute any operations before executing the gliding, which again, we're calling gliding here as well, or after executing the gliding. However, these glidings are not the gliding WMS glidings, right? They're just other glidings. And that's about it. in addition to it, these repository here should also have this account.conf file, which is this file here. So this file is the only configuration file that the experience would have to handle for submitting jobs to a specific site. So these variables here are defined and exported everywhere. By everywhere, I mean they will be present on the worker node and on the edge node. And you can actually see that all of them started with HPSS. You can see how committed it was to this name. So these are the main, not the main, but these are the variables that we'd like to highlight here. So the first one is a variable that we define the shared directory. So this is a shared batch system, the shared storage that we'll be using to transfer the files from worker node and edge node. You can define here which control pool you'll be willing to join. And you can specify CVMFS exec here, for example, to have a CVMFS deployment, even if you don't have CVMFS installed. Once we have that all in place, all you need to do to run the split starter is to log into an edge node, clone the split starter repository, and run these request lines.sh command. So these will contain all execution time configuration we'll need. So we need to specify a user to run the gliding, which VO we are running for, that's what the P stands for, which site we're running, that we see here is for Wilson cluster, which batch system that site runs, which is Lerm here, what queue you want to submit to. Sometimes it's called account as well. In this case, we're just using CPU to see here. And -E here stands for edge directory. So this is essentially where you want to deploy the software skeleton that you need to do the submission, so on, to store the logs, and basically everything you have, the job outputs as well, everything's going here. And this N here is how many jobs you want to submit for that specific site. So how many glidings you want to have there. So ideally, this script will submit the glidings. They will be queued up on the local batch system. Once they start running, they will report back to the configured control pool, and then they will act just as normal slots. I've been talking about the execution workflow of the split starter so far, but this is what it looks like. So right here, we have the input of those parameters that we just discussed. We call this request glidings.sh script, and this is all the operator interfacing part of it, well, that and the configuration file. So what this guy here does is that it will call this other script here, which will, based on these parameters here, decide which account configuration file you should use, because you can potentially have several repositories for different experiments. And then it will, using that, submit here inside an obtainer container, the edge starter. At the same time, it will submit a batch job that will contain this init start script here that will, again, queue up and wait to take hold of a worker node. Once it has a worker node, it will then start running. And all this script here does, well, besides executing the pre-job scripts, it will launch this launcher.py file here. So what this script does, it will be watching the storage system here, the shared storage here, for jobs that might have been downloaded from the edge node starter. So the edge node will be communicating with the control pool. When you get the job here, it will download the job payload on the shared storage. This script here will see the job, and then it will launch a starter on the worker node as well. It will actually do the work. This starter here will only execute the job once it's done. It will save the output back in the storage system here, and it will be transferred back to the SCAD. So the accomplishments that we had with this work was basically we were able to produce a template system that was lighter and more generic and that can actually be reused. We simplified the code base a lot because now we have less replication. We reduced the footprint of the split starter on shared storage. Actually, this was a specific request from operators that were afraid that sometimes writing logs, for example, before we had the jobs actually writing logs to the shared storage, they were afraid this could actually affect the storage, even bring it down. And we were able to accomplish our goal here, which was to run jobs on Summit, and actually it was a cluster as well. There was an added bonus there. So as I said, this was mostly a report of the work that we had done. Now this script will be handed out to Hyung-woo, who will be taking over from us, and we'll be working still at Fermilab on a different group. And I left a few suggestions here to future improvements that we might do. The second and third ones here are simple, right? So we have to specify the batch system when we execute the request gliding script. That can possibly be moved into the account.config file, so we have one less parameter there. That's something to consider. We could also try, and now that we have more time, consider using glad finally to avoid having to write manually those scripts to interact with batch systems. But the first one here is the biggest concern that I have. So the problem is, because the way it works, let me just go back a few slides here. So what happens is, they started running on the edge node here. We will start running immediately when you call the local gliding script here. It will report back to a control pool and make itself available to run jobs. If you have jobs queued up and they match this slot here, they will be assigned to the slot immediately and show up as running. The problem though is they won't be actually running, because most likely the worker part of the starter that we submitted here to the batch system is still in the queue, so it didn't start running yet. So for quite a while, we can actually have those jobs there showing as running on the control queue when they're not actually running. They're just on a separate or on a different queue in a different batch system. This is something that we haven't been able to solve yet, but would be really nice to solve it before we actually go into a bigger scale production with it, because it can be really misleading for the user to see jobs running when it's not actually the case. That's all I had for this presentation. Thank you.